Hello. In this lesson we will discuss heat capacities of gases. Tell me first of all, what is the meaning of heat capacity? We discussed the difference between specific heat and heat capacity. Well, heat capacity is mass multiplied by specific heat. In other words, it's a measure of the amount of heat required to raise the temperature of a given amount of substance by 1 Kelvin. So, in this lesson we will discuss heat capacities of gases. When you talk about gases, there is a little problem. The problem is the amount of heat required to raise the temperature of a given amount of gas by 1 Kelvin depends on whether the gas is kept at constant pressure or constant volume. The two quantities of heat are different. Therefore, we have two types of heat capacities for gases. We will talk about these two types of heat capacities in this lesson. Heat capacity of a substance is a measure of the amount of heat needed to raise the temperature of the substance by 1 Kelvin. And we can represent C as mass of the substance divided multiplied by specific heat, which is m times small c. We know that, we have used that earlier. If a quantity of heat dq added to a substance increases the temperature by dt, then dq equal to c dt. Do you understand that? If C is the amount of heat needed to raise the temperature by 1 Kelvin. So if you want to increase the temperature by an amount dt, the total amount of heat you need is C times dt, where C is the heat capacity. What's the heat capacity? It's a measure of the amount of heat needed to raise the temperature of the whole object by 1 Kelvin. So if you want to raise the temperature by a quantity dt, the quantity of heat you require is C times dt, heat capacity times dt. Or we can write this as C, the heat capacity, is dq over dt. Now actually, this is a better definition of heat capacity, isn't it? The amount of heat required per Kelvin rise of temperature, dq by dt, the rate at which heat is used in raising the temperature. That is the definition of heat capacity. Alright, so keep this. C equal to dq by dt, the amount of heat needed to raise the temperature by 1 Kelvin. The amount of heat needed to raise the temperature of a given mass of gas by 1 Kelvin depends on whether the gas is kept at constant volume or if it is kept at constant pressure. As I have told you earlier, these two quantities are different. Therefore, we have to define two types of heat capacities for a gas. What are they? The first type is when you keep the gas at a constant volume. And the second type is when you keep the gas at a constant pressure. Well, let's take the constant pressure first. Heat capacity of a gas at constant pressure is represented by Cp, C sub P. It stands for heat capacity at constant pressure. In the same way, the heat capacity of a gas at constant volume will then be C sub V. So Cp stands for heat capacity at constant pressure, and Cv stands for heat capacity at constant volume. Let's now consider heat capacity at constant volume. The amount of heat required to raise the temperature of a given amount of gas by 1 Kelvin when the gas is kept at constant volume. That is what we need to find. When a gas is kept at a constant volume, you know that when the volume doesn't change, there will be no work done. That means all the amount of heat you supply at constant volume will be used in raising the internal energy. If you remember, the amount of heat you supply to a gas will be used in increasing the internal energy and also doing work. Since when the gas is at constant volume, there is no work done. Therefore, all the heat that you supply to the gas at constant volume goes into increasing the internal energy. Therefore, we can say when the gas is at constant volume, dQ equal to du. And therefore, what is the definition of heat capacity at constant volume? It will be dQ over dt. That is the basic definition of heat capacity. dQ over dt. Therefore, dQ over dt is the same as du over dt. So, heat capacity at constant volume is a measure of the increase in internal energy per Kelvin rise in temperature. Isn't that interesting? The increase in internal energy per Kelvin rise in temperature. But dQ over dt is the heat capacity. Therefore, the heat capacity equal to du over dt. Cv, the heat capacity at constant volume, equal to du by dt, where what does du stands for? Du is the change in internal energy. Alright, I want to go back and ask you the same question I have been asking you several times. What is the internal energy of n moles of a gas? Do you remember that equation? The internal energy of n mole of a gas is 3 over 2 nRT. Is that right? Okay, we will talk about that as we go on. Now, before we talk about it, let's now discuss heat capacity at constant pressure. When a gas is heated at constant pressure, it expands. It expands means it does work, and in addition to doing work, its internal energy rises as well. So both these things happen when you supply heat to a certain amount of gas at constant pressure. Its volume increases, it means it will do work, and the internal energy increases, that means there is a change in the internal energy. So dQ equal to du plus dW. And what is the definition of heat capacity? Heat capacity is dQ over dt, right? Now, you know that Cv equal to du over dt, is that right? That's what we just found out earlier. So Cv equal to du by dt, therefore I can replace this du by what quantity? Du equal to Cv dt, is that right? So I'm going to say du equal to therefore Cv dt, and dW, I'm recalling all the things that we did earlier. Didn't we do this earlier on in the last lesson, that the work done is PdV? So using those two together, I can write dQ equal to du I replace by Cv dt, and dW, the work done, is PdV. And of course, remember, P is a constant here. Well, divide by dt. Why do you want to divide by dt? Because we are looking for dq by dt. dq by dt is the heat capacity at, well, this dq by dt is a measure of the heat capacity, whether it is at constant volume or at constant pressure. So in this case, when dq equal to du plus dw, where du is cv dt and dw is pdv, in this case dq by dt will be our Cp. So dq by dt equal to, I'm dividing each term by dt. So the left hand side is dq by dt. Cv dt divided by dt will be Cv, plus pdv divided by dt will be pdv over dt. Well, what's our next step? dq by dt is our Cp. So you have Cp equal to Cv plus pdv. Now, is it possible to replace this pdv by a more friendly term? Where do we go for that? Well, we go to our familiar equation. What is our familiar equation? The ideal gas equation. PV equal to nRT. All right, let's go there. We now find dV by dt using the relation PV equal to nRT. Well, P is a constant. So, if you find the derivative of left-hand side and right-hand side with respect to T, what will you get? Take the differential of both sides. What is the differential? The differential of V will be dV. The differential of T will be dt. Here, V and T are the variables. P is a constant. NR also is a constant. So, if you take the differential of both sides, we will get P times dV equal to NR times dt. There you are. P dV equal to NR times dt. And now if you divide both sides by dt, I can now produce P dV by dt. Divide both sides by dt, we get P dV over dt equal to NR. Well, you could have actually obtained the same relation from here, finding the derivative of V with respect to T. You see that? You can also do that rather than going through the differential path. Okay, P dV by dt equal to NR. That means I can replace this P dV by dt equal to NR. So what does Cp equal to? Cp equal to Cv plus Nr. That's a beautiful relation. The heat capacity at constant pressure equal to heat capacity at constant volume plus Nr, where N is the number of moles of the gas and R is, of course, the universal gas constant. Now, so, which of these is greater, Cp or Cv? Cp is definitely greater. Why? Why is Cp greater? Because when you supply heat to an amount of gas at constant pressure, that amount of heat is used in two ways. One, to increase the internal energy, and two, to do work. Whereas, when you supply heat at constant volume, there is no work done. Therefore, the amount of heat you supply at constant pressure is greater than the amount of heat you supply at constant volume. Cp is greater than Cv. By how much?